So in this example, we are going to solve the differential equation 2x cubed plus 3y dx plus 3x plus y minus 1 dy equals to 0. First order, first degree differential equation. And as the header up here suggests, we're going to be expecting this to be an exact equation. So this equation in question is in the general form of some function m in x and y dx plus some function n in x and y dy equal to 0. So in this case, our m function is this argument here in front of the dx, and then our n function is this argument here in front of the dy. So now we've defined m and n. Now to check for if the equation is exact or not, we want to take the partial derivative of m with respect to y. So in this case, the only term that has any y influence is this 3y. So the first derivative of that, or the partial derivative with respect to y, is 3. Likewise, we want to take our n function and take the partial derivative of this with respect to x. So again, the only term in this argument that has any x influence is 3x, so we take the derivative of that, it's 3. And as we see, the partial of m with respect to y and the partial of n with respect to x are both equal to 3. So therefore, by definition, this is an exact equation. So this is how we test for that, is if these two partial derivatives are equal. So since this is an exact equation, there are two different methods that we can use to solve this equation. The first is a more direct approach. So let's look at how that works. So the first thing we do is we define this new term mu of x and y. And the way we define that is we take our m function that we defined earlier and we integrate that with respect to x. So in this case, our m of x and y was 2x cubed plus 3y. And so we'll integrate that with respect to x. So the 2x cubed becomes 1/2 x to the 4th. 3y becomes 3xy. And then we're also going to assume that there was some function of y only, not of x, that originally existed in the original equation. So, that's entirely possible, because if you take the derivative of this with respect to x, which would take us backwards in this equation, if this had no dependence on x, then it would just be 0. So this is perfectly valid, and it actually works out for an exact equation. So now that we have our mu of x and y defined, we now want to take the partial derivative of mu with respect to y. So remember, we integrated in respect to x, but now we're taking the derivative with respect to y. So when we do that, the first term, 1/2 x to the 4th, has no y dependence, so it's 0. 3xy, take the first derivative of that. Of course, the y goes to 1, so we have 3x. And then we'll just signify that we're taking the derivative of whatever this function of y was. And so now we want to set this equal to our n function that we had defined earlier. And so when we do, that's 3x plus y minus 1. So now that we have this equation, we should be able to observe that we have a 3x on this side and a 3x here, so we could cancel those out. And then what we're left with then is our first derivative of our y function is equal to y minus 1. So we should be able to get back to our original phi equation by just taking the integral of this with respect to y, which when we do, we come up with 1/2 y squared minus y. So that's just the simple integral of this function here. And so now we can substitute this back into our original equation there for mu. And when we do, we have our first solution. Of course, we can simplify this by multiplying through by 2. And when we do, we get x to the 4th plus 6xy plus y squared minus 2y equals to some arbitrary constant. We could solve for the constant if we had some boundary conditions, but we do not. So this is the solution to this differential equation listed at the top. Now, like I said, there is a second method to solve an exact equation, and so this is done more by observation. And so we recall, when we have the chain rule, y dx plus x dy, when we have something in this format, that's just the derivative, again, utilizing the chain rule of xy. So when we look at our existing equation, we can regroup this. So we have our 2x cubed dx is here. We have our y dy here. We have our minus 1 dy here. But now our 3y dx and our 3x dy, we can rewrite here and regroup it to be 3 times y dx plus x dy. So this is the exact form we were looking for. So this being the case, we can now just integrate this directly. And when we do, as before, going term by term, it's just 1/2 x to the 4th, 3x y, that's this term here, 1/2 y squared here, and minus y equal to c, or again multiplying through by a factor of 2. You can see we get the exact same solution as we got before. So 2 different ways to solve an exact differential equation.